recording. So it's a welcome to the Colloquium. It's a pleasure to have Tomer Markovich with us. Tomer got his PhD at Tel Aviv University, and subsequently he was a Blatavnik postdoctoral fellow at University of Cambridge. And then currently he is a postdoctoral associate at Center of Theoretical and Biological Physics at Rice University. And coming August, he's going to start his own group at Tel Aviv University. And he's going to talk about odd viscosity in active matter, something that is of my research interest, and he has done a lot of interesting work in this subject. So welcome, Tomer, and looking forward to your talk, and hopefully we can meet later in person sometime.
Sure. Thanks, Shiram. Thanks for inviting me. It's a pleasure to be here. So unfortunately not in person, but I hope someday. Yes, okay. So today I'm going to talk about odd viscosity in active matter, and this work was done together with Tom Lubensky on Zoom, most of it, unfortunately. Okay, so a little bit about what I'm going to talk. So Shiram told me there is some portion of undergrad students, so I'll make some longer introduction. I'll talk a little bit about what is chiral active matter. I'll explain about Onsite relations and how they're related to odd viscosity and what do I mean by odd viscosity. Then I'll present a recent model that we had for a microscopic model for odd viscosity in 3D materials, which basically we write the kinetic energy in terms of the total momentum instead of center of mass, and I'll explain more about it. And I'll try to briefly give a short introduction to odd viscosity in biological gels and why we should expect to see it there, or when. And in the end, I will talk about something we're doing now, and this is actually showing that odd viscosity can be non-reciprocal, so it doesn't obey Onsite relations, and we find it from direct cross-graining of the kinetic energy. And this might hint, I'll talk about it later, on something that has been done in Vincenzo Vitelli group about non-reciprocal phase transition. Okay, so let's start. So chiral active matter is everywhere. We see it in bacteria, where the flagella rotates one direction and the head rotates the other. We see it in actomyosin network, where the motors are, they're also stretching the network or the fluid around them, but they're also rotating because they're walking on the chiral filaments, actin, or it's also happening in microtubules with kinesin. We see it lately in active spinners, where you have some micron-size magnetic particles in a rotating magnetic field. So there's some kind of gas of rotating particles, and you can even see it in millimeter-driven grains, where you just build them chiral, so they have this chiral shape like in here, and then you basically put them on a shaking table and they start to rotate because of their chiral shape. And so it's basically in every length scale, in synthetic materials, in biological material, it's abundant. So it's very interesting to understand the properties of those materials. So I want to talk about odd viscosity, but to do it, I want to do a short introduction about Onsite relations. So what Onsite said is something very interesting and simple. He said that the heat production rate, or the entropy, T times the entropy production rate, can always be written as a sum of some thermodynamic fluxes times thermodynamic forces. And then, if we're close enough to equilibrium, we can write the fluxes in terms, we can expand them to linear order in terms of the forces. So, but you can have two types of couplings. One type of coupling is dissipative coupling, when it couples flux to a force that have different time reversal symmetry. Or you can have reactive coupling, with coupled flux to a force that have the same time reversal symmetry. So dissipative coupling would be, for example, between the stress tensor, which is the momentum flux, and the strain rate. So the stress is even under time reversal, the strain rate is odd. An example for reactive coupling would be, for example, in liquid crystal, when the time derivatives of the director is coupled to the strain rate, and this is the shear alignment parameter. So this would be reactive coupling. What's happening is that this reactive coupling has to, Onsager says, it has to be anti-symmetric, and the dissipative coupling must be symmetric. So those are tensors, so Dij must be equal to Dji, and the reactive coupling has to be anti-symmetric. And then if you just put it back in the equation for the entropy production, you see that only the dissipative coupling contribute to the heat production, but not the reactive. So that's what Onsager said, but he said something else. He said that what happened when time reversal symmetry is broken. So let's say you have some kind of magnetic field in your system. So it's still a conservative force, but even the microscopic dynamics are, it doesn't obey time reversal now. So we don't expect it to happen in the macroscopic level like in here. So we extended his notion and said that the dissipative tensor even has to be symmetric only if you reverse the magnetic field too. But that gives you another option for this dissipative tensor. So you can have two cases. You can have a tensor which is even under time reversal. So if I change direction of the magnetic field, stays the same, and this tensor must stay symmetric to obey what we just said before. But you can also have an anti-symmetric tensor which is odd under time reversal. So then if I change I and J and change the magnetic field, I still obey the symmetry that Onsager said. Okay? So this actually looks like the reactive term. So even though it couples flux and force with different sign on the time reversal, because this coupling is odd on the time reversal, it's still reactive. So it's odd. So to make it more concrete, let's talk about viscosity. And this is how I can introduce odd viscosity. So as I said, the stress, viscosity is what relates stress to strain rate. So stress is the momentum flux, and the strain rate is the thermodynamic force, and the coupling between them, this is the Onsager coupling from before, like this Dij, just now every index is, instead of Ij, I have Ijkl. And Onsager relation now for this fourth rank tensor tells you that if I have time reversal symmetry, I have to have a major symmetry. So eta Ijkl has to be equal to eta Klij. So I have, if I change the first two and first last indices, there has to be, eta must be the same. But when time reversal breaks, which is always the case in active matter, which is what I'm going to talk about, you should expect to see something which is odd. So odd viscosity. So it takes a minus sign when you change the first two and last two indices, and it should also be odd under time reversal. So this is what I call odd viscosity, or everyone call odd viscosity. And
can I ask you a question here?
Sure.
So I want to understand, when you say time reversal breaking in this context, that you always have it in active matter, you don't mean in the magnetic field sense, right? You're meaning in some sense of entropy production.
So I mean in a sense that I have some particles or some entities that consume fuel and move wherever they want. And by doing that, they break time reversal symmetry. So it doesn't have to be a magnetic field that breaks it. I mean, the example that Onsager had in mind was magnetic field. But this will happen every time you break time reversal symmetry. This is allowed at least. Okay, I just give it as a simple example.
Just purely dissipative systems, you don't have purely dissipative systems in mind, right? When you talk about this,
So
because even dissipation breaks time reversal.
yes, but no, I'm not talking about. So dissipation, in the way I see dissipation itself doesn't break time reversal, because if I go back here, so dissipation is this coefficient. Okay, I mean there's nothing so in the microscopic dynamics, time reversal is obeyed in that system, right?
Okay.
So when you cause grain, you have dissipation because you don't track all the degrees of freedom, but microscopically, the system can still obey, still have time reversal symmetry. Right? Okay. But when I talk about active matter, this is what I call microscopic inactive matter already neglect how the matter became active, if you wish. So I have particles that moves because they want to move. I didn't say where they got this energy from. Okay, so I mean, this is where things. But this is the point of view I'm trying to take here. Okay, so microscopically, time reversal symmetry is broken, like what happened with the magnetic field, but for any reason.
Okay. Okay.
So so already, like it's now 25 years ago almost, Yossi Avron showed that all viscosity is compatible with isotropy only in 2D. So Z here is outside of the surface. So if I have a 2D material here, I have only one odd viscosity coefficient like that. And this is how the odd viscosity tensor will look. You can verify that it's odd under interchange of Ij and Kl. And what he also showed is that in 3D isotropic material, there is no odd viscosity. You just can't have it. Okay, it's not compatible. You have zero coefficient left to write a tensor with this type of symmetry. So there is no odd viscosity in 3D. So just to show again, if I have this odd viscosity and I want to write the entropy production, so like I did it in general sense before, you put inside the stress this eta even, which is the regular viscosity, and the odd viscosity here. And because this eta odd is odd under IJKL, and it multiplies the strain rate from both sides, it actually vanishes. So it doesn't contribute anything to the production like you expect. So it's a reactive coupling. And if it's a reactive coupling, I can hope to be able to write some kind of Hamiltonian formalism to derive this odd viscosity. And that was our goal in the beginning, at least. So we want to write some kind of Hamiltonian from which we can derive this odd viscosity. It's not dissipative. We should expect it to come from some something that we can, something deterministic we can write Hamiltonian for. Okay, so before I will show you our model, just a little bit of background on odd viscosity in active materials. So recently, there was a very large interest. I'm not showing all the recent papers, there are dozens, but most of them were focused in 2D, lately more in 3D, but still most of them in 2D in the context of active matter, especially because there it was compatible with isotropy, so you can talk about isotropic materials. In the context of plasmas with magnetic fields, there were discussion even 50 years ago about odd viscosity in 3D materials, but this is very different than what we're talking about now, so I will not talk a lot about that. Two important phenomena that I want to point out is that in 2D, there are no bulk waves in 2D odd materials, but you have topological edge states. So you can see that the surface states in those materials only propagate in one direction. The fact that if they're topological or not, this depends. So Shriram here did some work without any topological context and showed that you can have unidirectional states in odd fluids in 2D. But in a different work, Anton Soslov and others show that if you add something that can gap the spectrum, like say a Coriolis force, or if you have charged particles on magnetic field, then they prove that those states are actually topological. So this is very interesting, and this was actually verified experimentally in this system here with these rotating spinners. So they add some magnetic field and magnetic particles, and they can show that you have waves that propagates only in one direction, basically because they move faster when the curvature is higher. So they can actually show that experimentally. So that's very interesting. So we should expect to see very interesting things in odd viscosity in 2D. And what we're trying to do is ask, can we write some Hamiltonian that will give me odd viscosity, some microscopic model for that, and what happened in 3D. Okay, so the model, so the way we were trying to approach the problem is the following. We said, well, let's look on the total momentum, because we know from this very early work by Paul Martin and colleagues that when you write the total momentum, so I have particles and each particle is composed of many atoms and each atom has its own momentum. And if you cross drain that, what you find is that the total momentum equals the center of mass momentum plus half curl of the angular momentum. So we thought that this will give us something interesting. And the reason is that if I write, so first, before I say that, when this total momentum actually gives you the correct angular momentum of your system. So R cross G is R cross the center of mass plus the internal angular momentum of each particle. But the reason we did it is because if I guess that the Coarse-grained Hamiltonian is just the total momentum square divided by 2 rho, instead of the center of mass momentum square divided by 2 rho, then I have this extra term, which coupled angular momentum and vorticity. In an earlier work by the group of Vincenzo Vitali, they showed that using this term, they can get odd viscosity. So, but here we do it in a microscopic way. So we just say the Hamiltonian is the total momentum squared and not just the center of mass. So the kinetic energy counts also the angular momentum now. And just by doing that, we get this extra term here, which couples vorticity or flow of the center of mass and the angular momentum. And we will show that we can derive from this Hamiltonian the odd viscosity. Okay, so just a comment before I go there. So why another reason to go to the total momentum stress is that when I actually measure the stress, so if I try to shear my system, okay, or if I try to move, I exert some force on the boundaries of some system, the force that I measure is the force that is related to the flux it's the stress, so the flux of total momentum. It's not only coming from the center of mass. So you can see it in a very simple example in this very simple paper by Garwin. What he had in mind is just a ball. So it was a super elastic ball that can collide, that has elastic collision, say, with a wall, but it can also spin. So there's no friction in this problem. So what happened is that if you just do conservation of linear and angular momentum, you see that unlike a point particle, that if it will hit the wall in some angle, it will just bounce back in the same angle. Because this particle can rotate, what happens is that it bounces back in a different angle. It's even easier to say that if you just spin it but throw it directly down, it jumps up in a different angle. So this is not what you would expect from a point particle. And it's also clear that there is some kind of shear forces here happening on the surface, because otherwise there's no way that this ball will move to the left, right? So there has to be some force in that direction. So if I want to measure, if I want to measure the force on that wall, it has to take into account somehow the fact that this ball can rotate. Okay, so it has to take into account the total momentum. So center of mass stress can be measured indirectly, but definitely in simulation, but not directly from just moving the boundaries. So you can use, for example, this Kirkwood formula, and you can track particles that hit the wall and do some indirect measurement, but this is not the force on the wall. So that's important to understand. That's why we guessed that we should use the total momentum here and not just the center of mass. Okay, so to get the equation of motion, we use something that is just the Poisson brackets. We use the coarse-grained Poisson brackets. So let me explain the idea behind it. So this was used a lot in dynamic critical phenomena. So this is a very well-known method, but the idea is very simple. So the microscopic dynamics obey Hamilton equations, which can be written in terms of a Poisson bracket, where I have some Hamiltonian, and any function propagating in time can be written like that. So f depends on some generalized coordinates and generalized momenta, and so does h. Okay, after coarse graining, so I have fields, and those fields depends implicitly on those coordinates and momenta, and you can write them in terms of, I think this is in terms of the Poisson brackets like this, where now h is the coarse-grained h, so it's a functional of the fields, and phi are functions of fields that depends on space. And these Poisson brackets are the coarse-grained Poisson brackets. So they are, you basically write the microscopic Poisson brackets and then coarse-grain them, and I will explain what I mean by coarse-graining. Okay, so to do that, I have to know first how to coarse-grain, and I have to know the coarse-grained Hamiltonian. You can guess it, or you can derive it microscopically. But there are two important things to note about that. So first, the Poisson brackets only gives reactive terms. And because by definition, this is all something deterministic. The coarse-graining itself neglects a lot of degrees of freedom, and this is where dissipation comes in. And we're not going to derive dissipation in what we do. I will just put it by hand like is commonly done. But you can derive dissipation in other means. So just before we go on, I just want to say, what do I mean by coarse-graining? Because coarse-graining could be a normalization group coarse-graining, where I just divide my space into boxes, and in every box I say, well, the average, what happened is the average in that box, and so on and so forth. But what I mean is more in a fluid-like or continuum mechanics way of coarse-graining. So I'm basically trying to ask, I have a point in space here, and I want to ask what is the value of the field in that point. So I just have some function. It could be a Gaussian, it could be some Heaviside function that says around that, it has to be smooth function. Around that point, I'll just average what's happening around that point. And I will say what happened, this average gives me the value of the field at that point. So every particle can be, can have a role in many points, right? So if I take a point here and I'll take a circle, so it will have the same particles. So particles will affect a few points in space, but this will give me smooth functions like I want. But we're doing something more than that. And I also want to know how to coarse-grained functions that look like that. So this could be, for example, the Hamiltonians. I have the moment P alpha, for example. So if I want to write the kinetic energy, I want to write it in terms of the coarse-grained field. Okay, so I write it here in general terms. So if I have some sum of A alpha, B alpha that are in some point in space are alpha. I want to write it in terms of the coarse-grained field A of R and B of R. And the way we do it is the most simple way you can have in mind, and I just replace B alpha by its average within this coarse-grained volume. So it's an approximation. So I just replace it by A of R divided by the density. Okay, and this gives me that the coarse-grained field here, if it has this form, would be just A times B, the field A, the field B divided by the number density within that region. So you can check that it works in, say, the kinetic energy or in other cases, but this is obviously not exact. That's an approximation, and that's how, this is what I mean by coarse-grained. It's the simplest way you can have in mind. So you can have deviation from this average, and if you want to discuss that, and I will not discuss that today, you can add noise, and this will be some kind of fluctuating hydrodynamic type of equations. So you have some stochastic equation. Now you can do it. At the moment, I'm just interested in the mean field behavior. Okay, so now that I told you what I'm doing and how I'm doing it, let me tell you what we got. So we just used this Poisson bracket formalism, this coarse-grained one, with the Hamiltonian, which was just G squared over 2 rho, the total momentum. And we added dissipation by hand, but just by doing that, all viscosity just comes out. It's just a result of doing the Poisson brackets of carefully, but that's all. And the all viscosity coefficient is just proportional to the angular momentum. And the same, while doing that, you also get the dynamics for the angular momentum. And if I add some, say I want to have some torques in my system, some activity. So I have some external torques because of magnetic field, because of some internal mechanism that I will discuss later in the context of biological gels. So in that case, I will have some average angular momentum. So it won't be 0. And then an angular momentum behaves very much like a magnetic field, and it breaks transversal symmetry. It also breaks parity. And this is what gives rise to this odd viscosity. So if I don't have torques, L, the angular momentum, relaxes usually very fast to 0, and the odd viscosity goes away. But if it's there, I will have odd viscosity. And this is coming just from Hamiltonian equation. So if I relax the angular momentum and I have some, say, homogeneous torque in the system, then I have some constant angular momentum, at least to the 0th order. So I have some, so external torques or homogeneous torques will give me constant odd viscosity. But I told you before, but this is true in 3D here. All I'm talking now, I didn't say anything about dimensions. L can be in any dimension. And I just told you that all viscosity is incompatible with the isotropy in 3D. But the reason it's there is because the fact that I have angular momentum breaks rotation invariance. So when people started thinking on odd viscosity, they thought about it in more of in quantum quantum Hall systems actually, and there the magnetic field or the spin was it doesn't break the isotropy of the system. You can still have an isotropic system that has odd viscosity because of the magnetic field, but here in classical materials, the fact that I have angular momentum means I already have a non-isotropic system. I already break rotation invariance by definition. Okay, so this is very different from quantum Hall fluids, and we should expect to see it also in 3D, in active matter, at least in classical active material that break rotation invariance and time reversal symmetry. So we have odd viscosity. What else can we say? what we did is we tried to understand something about the mode structure in that system. So we wrote the linearized dynamic in the Fourier space. And what we see is that we have these two blocks here. So I have the transverse block here. So V1 and V2 are two transverse velocities, and VL is the longitudinal velocity. So in the direction of the wave vector. And I assume L is on the Z direction and that it is constant, say because of some kind of external field. So you can solve the eigenvalue equation. It's a quadratic equation. It has an analytical solution, but it's still very hard. But if I assume it's inviscid, so if I don't have any viscosity in my system, then this dynamical matrix is actually Hermitian, and the eigenvalue equation is biquadratic. So I can solve it analytically very easily, and I can show that there is 4 probability modes, 2 transverse and 2 longitudinal. And what's interesting is that K perp, so K which is in a direction perpendicular to L, couples those 2 blocks. Okay, so this makes things a little bit more complicated, but at least in case of compressible odd materials, but we can get everything analytically, and we can see how the sound velocities or the excitation spectrum looks like.
Or can I ask you a question?
Sure.
So when you're doing this calculation, are you doing it for the center of mass or the total momentum?
Total moment.
Okay,
So,
because this is exactly the question I'm gonna ask now. So when you go from one to the other, you neglect higher order terms.
higher order derivatives.
Yeah, higher order in derivatives.
Yeah, I neglect higher order in K if you want.
Yeah. So just to simplify the discussion here, I can do the same calculation in 2D and say that I have odd viscosity proportional to density, or I can have a odd pressure.
What do you mean to density? Just why to density? So this works also in 2D.
Just to simplify my argument, let's say that this Ln is along the z direction and is proportional to the density.
Okay.
Constant times density.
Oh,
And I know that in 2D, there are 2 ways we can do this calculation using the proper odd viscosity, and you get some dispersion. When you do it for odd pressure, which would have been the same as having this equation in the center of mass, you don't get the same dispersion unless you keep the second order terms.
So okay, so 2 things. First, this model doesn't give you odd pressure, right? You see, there's no odd pressure. So in 2D, just write Z, just remove the N, and that's a 2D equation. So this works for 2D, right? So
Correct.
In 2D, our model doesn't give you odd pressure at all.
It does for the center of mass momentum.
For the center of mass, it also doesn't. For the center of mass, what happens, I didn't show it here, it gives you only 1 out of those 4 terms, actually, but not the odd pressure. I will talk about the odd pressure later, but so when L is constant, you can manipulate things to look like odd pressure, maybe.
We perhaps can discuss it later. Sorry.
No, it's fine. It's a good question. I will talk about pressure, but so I can go to the center of mass from here. I didn't do it in purpose. In the center of mass, what happened is that I only see 1 out of these 4. I don't remember which one exactly, but Onsite relation doesn't seem to hold. And yes, and I do neglect higher order terms. So if they are important, I wouldn't know why, but we can talk about that. But odd pressure can appear in other in other situations, and I will say a few things about that later. Okay, so for now, assuming we don't have water pressure, and that is our model or the result of this specific model, I have this matrix, and I can find the eigenvalues, and I can find the dispersion relation, and the sound velocities for this specific model looks like this. So I only show 2 out of the 4 sound velocities. Minus of this is also a solution, because this is a biquadratic equation. I mean, every solution has its minus sign. It's also a solution. So this is what you see here. And this is how it looks. So alpha is the angle between the wave vector and L. And this is how, when I increase L, this is how it looks. S minus is always maximal at alpha equals 0, and S plus is always maximal at 45 degrees. And these sound velocities are very similar to what you see in columnar liquid crystal or pneumatic elastomer. So I'm trying to show it here. Basically, it's similar in the sense that there is some angle in which one mode just vanish, and then it's maximal 90 degrees away from it, and there's a mode that is never vanishing like this. Those modes always mix, because of this caper, they always mix transverse and longitudinal modes, exactly because of this caper. So because of this, so those 2 blocks are mixed all the time, except for in very distinct situation, which is when alpha is 0. So along this line, where in the normal case, where KL is smaller than C, the sound velocity, this is the normal case, then S plus is the longitudinal mode and S minus is the transverse mode. But you can imagine cases in which L is so big that you can go, at least theoretically, to this case, and then they actually switch. So S minus will be the longitudinal one, and S plus is the transverse. So it's not a simple, you can't simply separate them because of this quartic equation you have. And along this line, the transverse mode is 0. So you only have longitudinal modes when alpha is 0. So when you're exactly in 90 degrees here. So when K is perpendicular to L. So it depends on those in this exact direction, what type of mode you get. But those modes propagate in the bulk of this material. So this is very, very different from 2D. Now, okay, so that's not only happening on the surface of the material. So you can analyze more you can get some regime diagram of what happened when viscosities are not 0. So in the general case, so it is the same plot here, but now I do it numerically because there's no reason for me to try and understand things for a quartic equation. So I mark by blue regions in which I have 4 propagating modes, in black region of 2 propagating modes, in red regions where there are no propagating modes. And all of these plots are for viscosities, kinematic viscosities, which are small, 0.3, so smaller than 1, and some value for the so-called second viscosity. So it could be smaller or larger than 1. So I just want to say, these plots has to be thought of as being plotted for finite wave number, because if we want to think about what happened in the hydrodynamic limit when K goes to 0, the only place this is relevant is in this subplot very close to the origin here, where I have 4 propagating modes. So the blue regions basically tells you that, I mean, you have some damping, but it behaves as almost as invisible. So there is damping, but waves do propagate in both transverse modes and longitudinal modes. The black regions tells you that you can't have any transverse mode propagation, and these are just the regular longitudinal modes. And what happened is that even if the viscosity is very high, such that for small angular momentum, we don't have any propagating wave. If I increase L enough, I will always get to a region in which I have some longitudinal waves that propagate. So, I mean, this is not very interesting, but I just want to show that you can have various region, and you can have, and this should have region that there are no modes propagating that doesn't have to be connected to each other. So this is quite complicated structure, but you can get that even analytically, and you can understand exactly what's happening here. But maybe more interesting than that is this nice comment that I think it's nice, at least, that talk about how the coupling that of L to the various velocity direction, longitudinal or transverse, depending on how things break time reversal and parity. So in a node fluid, you can think, so you can say, you can write what is the time reversal signature and the parity signature of those three directions of propagation. So you have the longitudinal velocity is odd under time reversal and even under parity. It's even under parity because it equals V dot K. So it has to be even under parity. V1 is again odd under time reversal and even under parity. And V2, which is basically K cross V1, is odd under both time reversal and parity. So if I want to couple it to this term, to L times K K parallel, which is odd under time reversal and odd under under parity, I can only couple V1 to V2 dot. So V2 dot would be even under time reversal and odd under parity. Multiply this by minus minus, and you'll get that it has the same signature as V1. So because this is reactive coupling, I expect to have time reversal when after this coupling. So you can have those coupling here, and there are coupling that we don't see between LK parallel and V longitudinal, for example. So this block here is not, we don't see it in our model, but it is possible to see it. But for example, you cannot couple LK perp to V2. I mean, this coupling is not reactive. It will break this structure. And what's nice is that this transverse block looks very much, or it's very similar to what happened in spin waves in magnons. So MX and MY behaves similar to V1 and V2, not in the sense that they have the same time reversal and parity signature, but in the way they couple to MZ, which is like the way they couple to LK parallel here. The difference is that for magnons, the dispersion relation is isotropic because M rotates under different groups than the special points, which is not the case in odd fluids. So here the dispersion relation is always anisotropic because L rotates under the same group as the special points. So this has similarities, but they're not exactly the same. And when we look, I will tell you in a few seconds about incompressible odd fluids, then we will see exactly this dispersion relation. Okay, so let's go and ask what happened when the fluid is incompressible. So when it's incompressible, I basically I decouple those two blocks because I don't care about the longitudinal block. VL is just 0. And then the odd incompressible Navier-Stokes equation looks like this, where I have this P tilde here and this L dot grad omega term. So what is P tilde? P tilde is the mechanical pressure. It's just a diagonal part of the stress. Okay. If I will measure the pressure in that system, if I'll just try to squeeze my boundaries, I put a piston or something, this is what I expect to measure. L dot omega is just L dot omega, the angular momentum times the vorticity, and P is what I call the thermodynamic pressure. So it's the pressure that comes from the free energy derivative with respect to density. So this is so this is just dF dV, if you like, minus dF dV, the free energy. And another comment is that this term doesn't appear in 2D at all, because in 2D this gradient, this gradient is in the direction of L, and in 2D it's outside of the plane. So and there's no fluids there. There's no fluid outside the plane, so there's no derivative in that direction. So this term vanish. And if this term vanish, and this flow is incompressible, then the bulk flow is actually not affected by odd viscosity, because the pressure is just a Lagrange multiplier that tells that change itself to make sure that dV is 0. So I think Shriram already pointed out in a paper with Sasha Abanov, and they pointed out that only when you talk about boundaries where odd viscosity appears in those types of systems, in incompressible 2D odd systems. But this is very different in 3D. So in 3D, I have this term, which will make the equation actually look very different. So I should expect to see very different terminology in 3D. Any question? Okay, so for example, we checked what happened to Bernoulli's law. So again, Yossi Vron already showed in his paper, very interesting paper. So I look on this equation in steady state without viscosities, and he already showed that it works in 2D, and it actually works both for the mechanical pressure and the thermodynamic pressure. So in 2D, what happens is that this right-hand side is 0. So P tilde plus half rho V squared is constant. So this what tells you that this is the Bernoulli principle. So P tilde, the pressure plus half rho V squared is constant along a streamline. And in 2D, the vorticity is conserved along a streamline. So L dot omega is constant. So this actually also works for the thermodynamic pressure. But that doesn't work in 3D. In 3D, these terms makes everything, it basically tells that Bernoulli's law doesn't work at all. Okay, because once it's not 0, the P plus half rho V squared is not constant along the streamline. And actually, we can show that Kelvin circulation theory also breaks down in a very similar manner in 3D, exactly because of this term. Okay, so the phonology is different, and we expect to see other different phonology. For example, lift and Magnus force should also be different if you look on 3D materials, odd materials, which is not the same as in 2D. So very different. And I also want to say another word about the mold structure now for these incompressible fluids. So for incompressible fluid, it's very easy to solve the mold structure, because I go back, I only need to solve this block. And if I don't, and this is very simple. And what we find is that I have only transverse waves, obviously, and they are damped because they have some viscosity, but they can propagate because of this LK parallel. And the polarization of these waves is circular. So we can find the eigenvectors, and they look like this. So it's just like the electromagnetic wave. So they just rotate like this. Yeah, I'll skip that because I want to go to other things. So, okay. So I wanted to say a few words about odd viscosity in biological gels. So usually when I talk about chiral activity in biological gels, I'm talking, so biological gels, I'm calling a very general group of materials. So anything from actomyosin networks to even bacterial suspensions that are densely packed. Okay, but usually but most importantly, I want to talk about active gels in the sense of actomyosin, or that has motors, that they are the active ingredients there. So, and the reason I want to talk about that is because it's recently was suggested that this can play a very important role in many things. For example, in this paper by Naganathan from 2014, what they measured what happened in C. elegans embryo, and what they tried to, so they highlight the myosin here. So the myosin is there are motors that basically pull on the actin and they twist it also. And what they showed is that those things create, and I will do it many times this movie, they create this type of torque, macroscopic torque actually, in this embryo. And what happened is that they rotate this nuclei here in the middle. So it's easier to see on the right hand side here. So you see that this actually rotates quite a lot. And what they do is that they treat it in different ways. So they can inhibit the myosin activity. So this is what happened a little bit here. And they can enhance it. This is what happened here. And by doing it, what they show is that if this was the line of the nuclei in the beginning, and this is the line where the nucleus points after the rotation, so they can show that the myosin activity actually makes this thing rotate. So, and they claim this drives left-right symmetry breaking in how the cell is formed. So like understanding what is left and right in that cell. So this is just an example, but for me, what I want to say is that I want to understand more about what happened for chiral activity in biological gels. And to do it, I have to talk about angular momentum, because this is where torques will come into play, like torques like they show here. So things get quite complicated in general, because when you talk about torques, and if I don't have point particles, if I have some elongated particles like in here, you can have different type of surface torques. You can have torques that comes from some kind of spin-spin interactions. So I have two rods that they want to spin together. But you can also have center of mass forces that operates, like in here, that operates in a way that creates some macroscopic torque on your system. And they do not enter the equation in the same way. So those type of surface torques that comes from center of mass forces actually do not appear in the angular momentum equation at all. This is, well, I didn't cite it here, but this is in Landau-Lifshitz elasticity. They show that only the part, the antisymmetric part of the stress that cannot be written as a divergence will enter the angular momentum equation. Only this creates real torques in the system. Why is this interesting? Because let's say I want to model a bacteria or a myosin motor. I have many ways of doing it, because a torque is not as simple as a force. A torque by definition is a complex structure. It has at least two forces. So if I want to, so here I'm talking about internal activity. So things has to have, the total torque must go to zero. So it has to be some kind of torque dipole. It can't be a monopole. So I can have a general torque dipole like in here. So I have a torque monopole to one direction, another torque monopole to the other direction, so something like this and like that. But I can have also a force quadrupole, an antisymmetric force quadrupole that will look exactly the same. Or I can have some mixture of a torque monopole and a force dipole. antisymmetric one. And the thing is, those two, for example, they look exactly the same. And this one looks a bit different. So I have to understand what I want to talk about. So this, for example, a modeling like this would be very useful to model spirochetes. So some bacteria that has internal flagella instead of external one. So I want to focus about things that are actually coming from talks. So I mean, it will also work here because, but the reason I want to do it is because those things will lead to odd viscosity also in those gels. And the reason is very simple. So if I assume I have those kind of talks in my system, okay? So let's look on an actomizing gel. And let's say I have a lot of motors like that, and they are oriented randomly. So on average, the system is isotropic, at least in some large scale. So I can write the torque, the mesoscopic torque in that system, and with the average over all the directions of all these torques, essentially. And this looks like this. And if you average that, what you find is that in an isotropic gel, the torque is just proportional to the gradient of the motor density. So why is that interesting? First, it's inhomogeneous, but it is isotropic. And what's happening in that case is that the angular momentum equation has this torque in it that depends on this gradient of the motor density. And if I will relax the angular momentum as I did before, for the simple case, I will find that I have angular momentum, which is non-zero, but it's also inhomogeneous. So we should expect to see, and odd viscosity still appears immediately as I have angular momentum. So yes, so I should expect to see odd viscosity here. How long do I have left? I think we should be wrapping up soon, right?
Yeah, I mean, to finish whatever you have started, if you have any more slides.
Yeah, I will say just something new that's not published yet, because you asked about odd pressure, so I want to say something about that. So that was very nice, and everything worked really well, and we saw on-target relation, and everything was fine, and we can get odd viscosity from a microscopic model in 2D and 3D, and understand everything. But then we said, okay, so let's just let's be more direct, and let's just cross-grain the kinetic energy directly. So this is the kinetic energy written macroscopically for all particles. We used our formalism to cross-grain it. And what we find is that the term that we wanted to have that gives odd viscosity now actually appears as a boundary term. So if I look in the bulk or in a system with periodic boundary conditions, this term doesn't do anything. So the Hamiltonian actually look like the regular Hamiltonian that has a center of mass Gc squared over 2 rho plus half L squared over 2I if it's isotropic. And there is no this coupling term that gives us odd viscosity. So you derive the equation for this Hamiltonian and just get the regular Navier-Stokes and the regular equation for the angular momentum. That's not interesting. So where did the odd viscosity disappear? So it didn't disappear. What happened if you write the total momentum equation? So this is the center of mass. I just write this equation, G, which is Gc plus half curl L. So I use this and make everything write Gc in terms of G. And I go through the algebra. What I find is this. So that's the result. So this is still something we're working on, but what we find is that you do have odd viscosity, but you have other terms. You have terms which are the gray ones, which do not appear in 2D because they couple things to the direction in which L is pointing, so outside of the plane. So it basically couple vorticity to shear, to all 3 shears in the Z direction. You can check that. But you also have odd pressure that couple vorticity to pressure. So this does appear, but it only appears in this case, if I actually go through this formalism, when I actually cross-grain the Hamiltonian directly. So I'll go for that quickly. We do the same thing, linearize Navier-Stokes, the old Navier-Stokes equation. What's happening now is that the dynamical matrix is not Hermitian, which is very, very strange. So Onsite relations are broken now. Every time you will have a longitudinal wave, you will get a transverse wave that follows it. But you don't get the other. This is because this odd pressure. But the other way doesn't happen. And what's more than that, there are no bulk waves in this system. So I'll say it quickly. There are other reasons to believe that odd viscosity will appear because of interaction and also because of fluctuation. And if we will add odd viscosity to this equation here, so we'll add another odd viscosity that comes, say, from interactions, then we'll have something like this. This is written in dimensionless form. So this is not Hermitian. And what's interesting, it has propagating waves, but it can also have instability. So I'm doing fast because my time is up. So you can draw analytically the phase diagram, and you have regions of unstable modes, the modes that grow, and you have regions in which you have propagating waves, 4 waves propagating if it's inviscid. And what's very, very interesting is that those lines are lines of what is called exceptional points. So those are points in which we lose eigenvectors. So 2 eigenvectors coalesce and become 1. So instead of 4 eigenvectors, eigenmodes will have only 2. And in a very recent work in Vitelli's group, they show that those lines usually tells you that there is some kind of new phase transition. They call it a non-reciprocal phase transition. So we expect to see it here, but our system is very different than what they have. We don't have, our steady state is waves, what they call chiral. It's not some stable state or homogeneous state. So we still need to investigate that, but we expect to find something very similar here. So to conclude, if I want to talk about chiral activity, I have to talk about angular momentum. We first tried to write the Hamiltonian as just being the total momentum squared over 2 rho. So we had a microscopic Hamiltonian theory that gave us odd viscosity. It had Onsite relation in it. We find that you have anisotropic bulk waves in 3D, and that we also predicted that we should find odd viscosity in active jets. When you cross-grain directly the Hamiltonian, we find that we do have odd viscosity, but also odd pressure and other types of coupling, and those don't appear in 2D. And we find that dynamical matrix is non-Hermitian. So Onsite relations are broken just by the fact that I have angular momentum. So the fact that it exists breaks angular momentum. And then we also find that we don't have any bulk waves if we don't have any interactions. So unlike the first model. But if we have interaction, we have waves and instabilities regions. So maybe we have non-reciprocal phase transition. So that's it. I want to finish. I want to thank you. And I will, like Shriram said, I'm up in a new group. So if anyone wants to join, postdoc or PhD students, you're welcome in Tel Aviv. It's very nice there. And thank you very much for listening.
Thanks a lot, Tomer, for a wonderful talk. So are there any questions for Tomer?